Hello students, welcome once again to the discussion of waves. Okay, as you know, previous class we were discussing about standing wave formation. Okay, we had two waves. One is a forward wave, other one is a backward wave. We superposed both the waves in a medium, and what we got is a standing wave. Okay, and we dealt with the standing wave both qualitatively and mathematically. We got the expression for the resultant wave. Okay, that was y of xt is equal to 2a sine 2 pi x by lambda cos 2 pi dt by lambda. Okay, and we could analyze the physical consequence of this equation, and we got the concept of nodes and antinodes. Okay, nodes are the points at which waves destructively interfere and amplitude will be 0, and antinodes are the points at which waves constructively interfere. So the displacement will be maximum. Okay, displacement will be maximum. We have seen it. So, and we have also seen different applications of standing wave in our day-to-day life. Okay, so today we will once again come back to superposition of waves, but there is a slight difference. In this context, we have two waves. We have two different waves. Their wavelengths are slightly different. In the previous case, we had two waves. Their wavelengths were same, but they were moving in opposite direction, the same medium. Okay, in previous context we discussed two waves, identical waves. They were moving in opposite direction, and they superposed and they formed standing waves. But presently, in this present context, we have two waves. They are propagating in the forward direction, but the difference is that their wavelengths are slightly different. So we can say that they're of comparatively similar wavelengths. They are comparatively of similar wavelengths. Okay, so we consider two waves. Both are propagating in the positive x direction. So we are assuming that their wavelengths are lambda 1 and lambda 2. Okay, so we assume the first wave of this kind, y of xt. For the convenience, we can call it y1. y1 of xt is equal to a sine 2 pi by lambda 1 dt minus x. Okay, and the second wave is of lambda 2. So you can denote them like this: y2 of xt equal to a sine 2 pi by lambda 2 dt minus x. So both are propagating in the positive x direction. That is why you can see a minus sign, minus x, minus x. Okay, so what happens when these two waves simultaneously propagate to the same medium? We know that they will superpose each other. So when two waves superpose each other, what we do? We can add them. Okay, we can add them algebraically. So we write the resultant wave something like this: the resultant wave amplitude, or the displacement of the wave at any point along the horizontal axis will be y1 plus y2. What does y indicate? Y indicate the vertical displacement at any point along the x direction. So we have the full expansion, complete expansion of y1 like this, and we have the fullest expansion of y2 like this. So we can add them up. Okay, we add it together. So as you know, they are two sinusoidal functions, two sine functions. We can add them up and you can write them in the product form. For that, what we have to do, we have to take the amplitude outside. The rest of the thing is sine function. We have two different sine functions. You can see one is in the wavelength lambda 1 and the other one is in the wavelength lambda. When you add them up, you have to use the trigonometrical function sin a plus sin b equals to sin a plus b by 2 cos a minus b by 2. Okay. How do we take a and b? We can take a as the first argument, 2 pi by lambda 1 dt minus x. You can assume as a, capital A, and 2 pi by lambda 2 dt minus x as b. Okay, so there is no harm in it. So we took a and b. So then we can insert here a plus b by 2 we want. Okay, we want a plus b by 2. A plus b by 2 will give you pi dt minus x 1 by lambda 1 plus 1 by lambda. And what about a minus b by 2? Yes, of course, you have to subtract them and divide with 2. So you will definitely get pi dt minus x 1 by lambda 1 minus 1 by lambda. So now we got a plus b by 2 and we also got a minus b by 2. Okay, we can put them together. So we got the resultant wave. We get the resultant wave. Simple thing, very simple. We simply introduce the a plus b by 2 here and a minus b by 2 here, nothing else. So this is the expression for the resultant wave in product form. Understand? Okay. So we have a lot of advantage by writing them in product form instead of writing in summation form. This is a summation form, and the second one is the resultant equivalent product form. Okay. So now what we are going to do is, we want to get some physics out of it. We want to get some physical consequences out of it. So in order to understand this physics, what we are going to do is, we freeze the wave. Okay, freeze the wave means let us make the moving wave still for some time. In order to make the moving wave still for some time, just freezing. Okay, you take t is equal to 0. So the moment you take t is equal to 0, the wave gets frozen. Okay, get still, or just we are taking a snapshot of a moving wave. Okay, at that moment, what happens? You are putting t here 0. So obviously, the argument got modified. The argument of the first term, argument of the second term got modified, and now you can write like this: y equals some minus a sine 2 pi x by lambda 1 plus sine 2 pi x by lambda. Okay, this is a function. This is an equation purely in x. Okay, y is the vertical displacement, x is the horizontal displacement. Now you get a purely two-dimensional graph. This graph in this function shows how y and x are related. Okay, a is a constant, capital A is a constant, lambda 1 is a constant, and lambda 2 is also a constant. So obviously you can plot this graph. Okay, this is simple function in x and y. When you plot this graph, what you get? Yes, you get a plot like this. A very simple plot like this. Any one of you can do using an Excel file. You can give some value for lambda 1, lambda 2, and a, and if you plot, you will get the y plot like this. Okay. What does this plot indicate? It's a pure two-dimensional graph. You can see that initially we had two waves of constant amplitude. Okay, about a different wavelength or slightly different wavelength. When they start propagating in the medium, okay, you get some what is called some intermittent pulses, okay? Alternately varying intensity pulses. And, okay, a pulse, first a packet of pulse is formed, then again its amplitude 0, again next packet its amplitude increases and again the maximum. Okay, this process goes on as you plot the graph over infinite values of x. Okay, it never ends up. It never ends up. The more you take the values of x, the more number of pulses or packets of pulses you get. Okay, so that means by taking time is equal to 0, you got a very physically meaningful picture of a resultant wave propagating in the medium. Okay, here, as you know, it is not propagating now because we have frozen the curve. By taking t is equal to 0, we have frozen the curve. The moment you vary the time, what happens? This will give you a oscillating wave. Understand? We will shortly show you that oscillating wave. Okay, such pulse formation are usually called beats. Okay, we have so many examples to quote from our daily life about beats. We will come to that. Okay, we will come to that very soon. These are called if two such waves of slightly different wavelengths are superposed in a non-dispersive medium, then what happens? They form beads. Okay, here you can not only word non-dispersive. Okay, non-dispersive means whenever a wave of some definite wavelength propagates through a medium, if the speed of the wave does not depend on the refractive index of the medium, then we call it a non-dispersive medium. Understand? That means in a non-dispersive medium, all waves of different wavelengths will propagate with the same velocity. Understand? In a non-dispersive medium, all waves of different wavelengths will propagate with the same velocity. For example, vacuum is a non-dispersive medium for lights. You know, light contains 7 colors, and in vacuum, all the 7 colors propagate with the same velocity. So vacuum is a non-dispersive medium for visible light. Okay, so different examples are for there in different medium, different waves. For sound waves, you can discuss such a non-dispersive medium, or many other electromagnetic waves we can discuss. So that is another session to be discussed separately. Okay. So again, let us come back to the concept of beads. We had a function like this, where x and y are related like this, and if you plot, you get a graph like this in which the amplitude of the wave, you can see the amplitude of the wave is getting modulated continuously, modulated along the x direction. What is being in modulation? Modulation means the amplitude of the wave is continuously being changed, varied. Okay, this is happening here. Okay, we had initially two waves where amplitude were constant, no change for amplitude. But when they combine together and put in a medium, what happened? The amplitude itself get modulated in a specific fashion. Okay, in a specific fashion. So that is what we get from the plot. Okay, we simply made a plot and plot showed like this. Okay, so and we say that the wave looks like intermittent pulses of rapidly varying amplitude. Wave looks like intermittent pulses. Okay, each pulse you get, it's not actually waves. It looks like pulses. Separate bunch of waves going, so that we call as pulses. And its amplitude is also varying very rapidly. Okay, very rapidly it goes to maximum, then again comes to zero, again goes to maximum, again comes to zero. This way amplitude is going up and down. Understand? That is one of the important thing you can note from the plot. Okay, so far what we have done, we have two waves, one like this and one like this. Their wavelengths are slightly different. Again you can see this is a snapshot of a wave. Okay, so no time variation is shown both in the equation and in the figure. Both are still. So when you combine it, you get a resultant wave, a still wave like still wave, snapshot photograph will show. Okay, of course, you must keep in mind that we are discussing about a time-dependent function, a time-dependent physical quantity. We will very soon come to the time-dependent part also. For the time being, we took only the space-dependent part just to understand the phenomenon. Okay. Okay. So the resultant waves, you can see amplitude is continuously varying externally, and this is usually called the envelope of the wave. So there is two kind of variation. One is the internal variation that is here shown. One is the external variation. External variation is for the amplitude of the wave. Understand? And even within that envelope, the wave is oscillating with another frequency. So both things we have to discuss. So we need some mathematics to discuss it. Understand? Okay, let us do that. For that, you have the waves here with lambda 1 wavelength for the first wave and the lambda 2 wavelength for the second wave. Okay. And you already know 2 pi by lambda we call wave number and it's shown as k1, and 2 pi by lambda 2 we call as wave number k2 for the second wave. And omega by k we have already studied, that is equal to velocity. You can put these values here. So what happens? 2 pi by lambda 1 is k1, you place here, and 2 pi by lambda 2 is placed k2. Okay, we simplified the equation a little bit more. Now what happens? This is a sin a plus sin b form. Of course, you can write them in the product form like this. So we have written in the product form. So we get in 2a sin k1 plus k2 by 2x cos k1 minus k2 by 2x. Okay, so we have now a sine factor and a cosine factor. Okay, just modify, take the 1 by 2 outside from both arguments. So you have sin 1 by 2 k1 plus k2x here, and cos 1 by 2 k1 minus k2x. Okay, and you can bring cosine factor to first and sine factor to second, because we have some purpose. That is why we did like this. We brought k1 minus k2 factor to beginning and k1 minus k2 factor, that is sine factor for the second. Okay, so what is the purpose? Purpose is actually to interpret the physics of this. That is what the intention. The first factor 2a cosine k1 minus k2 by 2. This is called the amplitude factor. This is called the amplitude factor. This will decide what should be the instantaneous amplitude of the wave at different times. Okay, or at different values of x. And this sine factor will decide with what frequency this should oscillate. You can see inside the envelope there is an oscillation that is shown by sine factor, and the outside oscillation, external envelope oscillation, is shown with the first factor, that is 2a cos k1 minus k2 by 2. So this is called the modulation factor. The first factor is called modulation factor. The cosine factor in the above expression is called modulation factor. And you can also see it goes to maxima, then comes to minimum. Again maxima, again to minimum. So maxima of the wave appears when cosine factor is unity. That means whenever cos of this factor that becomes 1, a wave amplitude will be maximum. Okay, so that means you have to place them as 1. Okay, you know the maximum value of cos is 1. So whenever this is 1, this amplitude will be maximum. That is this point. Understand? Or this point. For every such point, that means for peak values, or in terms of antinodes, you can say whenever cosine of this argument become 1, its wave's amplitude will be maximum. You get a peak. Or for that to happen, what should happen? This angle should be an integral multiple of 2 pi. You know, cos 0, cos 2 pi, cos 4 pi. All those are, 1. Understand? Okay. So you can extract the value of x there. That means if this is to happen, at what all points on the x-axis this can happen. This is our x-axis. You keep in mind x-axis. At what all points this can be maximum. Okay, so that is x is equal to 2 pi by k1 minus k2. We have got it from there. Okay. And see, so we can write this as equal to for this is possible for n is equal to 0. This is possible because n is equal to 0 means here, okay, at the maximum peak, and n is equal to 1 again, you get the next peak 4 pi. Okay, n is equal to 1 will give you something called 4 pi. Okay, this way for every integral values of n you get a peak. Okay, so peaks corresponds to antinodes, antinodes. So these are for maximum value of x or maximum value of n. Okay, hope you understand. Maximum value of y. Sorry, what I told is maximum value of y. Okay, maximum value of y is shown here as x max. What does it mean? That is that x at which y is maximum. You don't understand it as maximum value of x. No. This is that x at which y is maximum. So this is a maximum value. So this is another maximum value. So every point you can write a x max. Okay, here y is maximum. At x max, y is maximum. So x max is equal to 2 pi by k1 minus k2. Where n is equal to 1, 2, 3, etc. Okay, so you can write any two adjacent points. You find the first two maxima, for example. And for any two maxima, you can take the first one as n simply, and the next point as n plus 1. Okay, so n plus 1, you place here n plus 1, and here n. So you subtract the second from 1, you get the distance between the adjacent peaks or adjacent antinodes. You will get the distance between the adjacent antinodes. So that will be simply 2 pi by k1 minus k2. You have to subtract this from this. You got 2 pi by k1 minus k2. Okay, this is the distance between two adjacent antinodes. Similarly, you can find the nodes. Nodes are the points at which the displacement is 0. Okay, 0. Displacement is 0. So displacement is 0 means you can rearrange it. 0 occurs whenever the argument of cosine is odd number multiple of pi by 2. Odd number multiple of pi by 2, where n is equal to 0, 1, 2, 3 like that. Okay, so you can write then x will be equal to pi by k1 minus k2 2n plus 1 by 2. It is obvious. Okay, so at these points, whenever x is satisfied this value, at those points y will be 0. Okay, we call it x minima. We call it x minima. At x minima, y will be 0. Okay, keep in mind this is the x-axis, this is y-axis. At x minima, here is one x minima, here is one x minima, here is one x minima. At x minima, this value will be 2. For the first point, you put n is equal to 0. For the second point, you put n is equal to 1. Third point, you put n is equal to 3 like that. So obviously, you can find the distance between two nodes. What you have to do, you take it as n, and the next one as n plus 1. So for n plus 1 and n, you can subtract. Very simple process. When you subtract them, you can see that this again is 2 pi by k1 minus k2. Previously, distance between two maxima you got as 2 pi by k1 minus k2. Now you got the distance between two minima as also 2 pi by k1 minus k2. So it shows that whenever such kind of beads are formed, that distance between two peaks or antinodes of the beads are 2 pi by k1 minus k2, and distance between two, the separation between two nodes are also 2 pi by k1 minus k2. So we can conclude that the separation between two adjacent nodes and two adjacent antinodes are equal. Understand? Antinodes are equal. Okay, I hope the idea is clear. So these are very important concept in superposition of waves. So that is shown here. Okay, equal distance. Now, what is the importance of these beads formation? So beads are very important in many instruments. For example, you have suppose you have two tuning forks. Assume that their wavelengths or frequencies are almost similar, comparable, and you excite them together simultaneously and keep, then you will see some sound variation. Okay, instead of getting constant vibration, you get a gradual variation in intensity of the resulting sound. Okay, so it will go to maximum and come to minimum, again go to maximum and come to minimum. So it has also a frequency. So the variation in intensity also has a frequency. So that's called beat frequency. Okay, we will come to the beat frequency now. For that, again let us write the wave together. Two waves superposition together, and we can write them in terms of wave number. You know 2 pi by lambda is k1, we have written here. 2 pi by lambda is k2, we write here. And k1v, we know k1 kv is equal to omega. We can place it as omega 1, we can place this one as omega 2. So we can write the resultant wave is equal to a sine omega 1 t minus k1x plus sine omega 2 t minus k2x. Simple form. Okay, in terms of omegas and t's also you can write the resultant wave. Okay, so you know again sin a plus b, sin b form is taken, so you can add in product form. So we get a new expression. So in which what is written, c plus d by 2 is written here, and c minus d by 2 is written here. Okay, we can again simplify them. For simplification, what we have done is, suppose we imagine that we have two frequencies, one is omega 1 and other is omega 2. Okay, and if we take a middle frequency omega 1 plus omega 2 by the middle of that. So we can say that they are separated by some delta omega. Okay, this is the middle frequency. In the picture it is shown here, omega 1 and omega 2, and middle one you take as omega. So omega 1, assume that it is omega plus delta omega, and omega 2 you imagine as omega minus delta omega. Slightly different frequency. And similarly k1 and k2 can be also written in the same formulas, k plus delta k and k minus delta k. So what about omega 1 plus omega 2, because we have omega 1 plus omega 2 by 2. So obviously that will be omega, and k1 plus k2 by 2 will be simply k. And we have why we have done all these things, because we want to simplify this equation, and so that we will get some physics out of it. We can derive, we can extract some physics out of it. That is why we are trying to simplify it. Even though this is not a complex equation, still in order to comprehend the idea, comprehend the physical idea, we are simplifying it. Okay. Again, of course, omega 1 minus omega 2 by 2 is delta omega. You can easily write from here. And k1 minus k2 by 2 is delta k. Okay. So we have all the ingredients now with us. We can input here. So you can see that this lengthy equation now got simplified. So now we have a y is equal to 2a sine omega t minus kx into cos delta omega t minus delta kx. Okay, so now you see the resultant wave is a time dependent function. So we need a graphics, a time dependent graphics to show it. So that is what is shown there. This animation clearly shows this way, because here we have time, we have space. Okay, in earlier slides we had only space dependent functions. We had snapshots, but here snapshot is not sufficient, because the wave is evolving in the time. So the resultant wave is shown here. Okay, so let us try to interpret it. Okay, let's try to interpret it. The first part, as I told you, cosine part is really indicate the amplitude. It takes into account the amplitude of the resultant. So this cosine delta omega t minus delta kx is simply showing with what frequency its amplitude, the amplitude of the envelope is changing. Inside there is an amplitude change, of course, but outside there is an amplitude change. Okay, continuously. Understand? So that is what is shown by this 2a cos delta omega t minus delta x. Delta x simply take into consideration of the propagation. Okay, it has nothing to do with the time variation. It is deal with the propagation. Okay, you can see 2a is here. You can also see that a is first a wave is of amplitude a, second wave is of amplitude a, and the third wave you can see at some points its amplitude will become 2a. Okay, whenever force factor become 1, its amplitude will become 1. Okay, that was discussed in the previous slide. Okay, this point, at this point we had a maximum amplitude, and this is time varying. Understand? Time varying. Okay, and the second part is discussing the oscillations within the wave, omega t minus kx. Keep in mind, this omega is mean of omega 1 plus omega 2. Understand? Mean. Whereas delta omega is the difference in the angular frequency. Okay. So the envelope amplitude is changing with the frequency of difference in the frequency, and inside the actual wave is oscillating with the frequency of average of both waves. We have two average of both frequencies, you can say. Suppose this is f1 and this is f2, then frequency of the resultant wave will be f1 plus f2 by 2. And whatever the frequency of this oscillation, envelope oscillation, or this one, you can see here, still forever. And this will be oscillating with the frequency of f1 minus f2 by 2 or f2 minus f1 by 2. Sorry, difference of this frequency. Okay, where negative sign is not important. We are simply dealing with the absolute value of the difference of frequency. Okay, nothing to do with the negative sign. Okay, so that is specifically shown here. This bracketed term shows the amplitude variation of the envelope. Okay, envelope. And the second factor shows the variation within the envelope. Variations within the envelope. Obviously, the variation of the envelope is comparatively very less compared to the oscillation within the envelope. Okay, because here oscillation frequency is delta omega, whereas here oscillation frequency is omega. Because of that, and these all are beautifully illustrated in this animation. You can see first case two waves separately, and the resultant amplitude, resultant wave is shown here, and its envelope is also shown here. How the envelope varies. So envelope is taken in account by this factor. Okay, once again reminding you, envelope is taken into account by this factor, and inside the variation is taken into account by this factor. And this is the resultant wave expression in terms of wave number. Understand? Using wave number, because in previous case we discussed in terms of wavelength only. Now we express them in terms of wave number, and this is more easily understandable. Okay. I hope now you have clear the idea both in the mathematical side as well as the physical side. Okay. And if you want to test an individual pulse, you can check it like this. Individual pulse, how each and every point of that pulse is formed, it is clearly shown here. In fact, what is happening is destructive and constructive interference. At each and every point, either it happens a destructive interference or a constructive interference. That is how the resultant amplitude at every point is observed. Okay, you note down here. You can see there are points of completely destructive interference, and there are points of completely constructive interference. For example, at this point, there is a destructive interference because both waves are going in opposite direction. Whenever waves are in the same direction, there will be a point of constructive interference, and you get the antinode point. Whenever the points are of destructive interference, that means displacement in exactly opposite direction, that will be point of destructive interference or point of node. Okay, so this animation shows a focusing a single pulse and investigating what happens at each and every point. Okay, and its mathematical correspondence is shown below. So again, we have already introduced the concept of beat frequency. How we will get the beat frequency? You already know omega 1 minus omega 2 by 2 is delta omega. So omega 1 minus omega 2 we can write as 2 delta omega. And omega 1, 2 pi f1, and omega 2 is 2 pi f2. So what you can do, omega 1 minus omega 2, you can write as 2 pi f1 minus 2 pi f2. That is 2 pi f1 minus f2. And f1 minus f2, that is equal to 2 delta f. From the figure it is here, 2 delta f. So delta omega we got. And omega also we know that is 2 pi f1 plus f2 by 2. So you can place them here. So we get the complete expression in terms of frequencies. First expression is in terms of angular frequencies and k's, and second one is in terms of real physical frequencies and k. Why this is taken? Because it shows what is the frequency of the envelope and what is the frequency of the wave inside it. F is the real frequency with which the composite wave propagates, and 2 delta f is the frequency with which the envelope propagates. There are two things, one is the wave propagates and one is the envelope propagates. Here real wave propagate with the frequency f, that is equal to f1 plus f2 by 2. Okay, that you know. And envelope propagates with a frequency 2 delta f. 2 delta f is of course equal to f1 minus f2. Okay, so we have amplitude part here. Okay, we can make them, we can assign them a value amplitude. Okay, instead of a you can give some other notation that may not be exactly correct. You can see, for example, you call it some m. Instead of a you can call it a m. Okay, m accounts for the amplitude variation of the envelope. So you can see from this equation the beat frequency is given by f1 minus f2. Okay, here the 2 delta f is the frequency difference. 2 delta f is the frequency difference, that is f1 minus f2. That is called the beat frequency. Beat frequency. This difference in frequency is called beat frequency. So what is actually that? Okay, that is the number of times the antinodes occur per unit time. Understand? Beat frequency is the frequency with which antinodes occur in unit time. Okay, it is written here with two slightly different tuning forks, for example, are excited, then beats can occur in which a periodic variation in sound easily can be heard. And this variation in frequency will be equal to difference in frequency of the fork. Understand? For example, for understanding this, suppose you have two frequency tuning fork. One is say 200 and other one is 205. Okay, 200 and 205. Then what will happen to this beat formation? That means you will see an intensity variation. How many times? 5 times in 1 second. 5 times in intensity variation. Okay, if you want to make it more audible, suppose you make some 2 hertz. Suppose you have a 24 for frequency 200 and another one is 202. Then how many times you will hear the peaks? 2 times per second. That means your beat frequency will be 2 hertz. That means in every second you will hear 1 time or 2 times the peak intensity value. Beat, 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 like that. Every 1 second you will have 2 beats sound. Okay, if the number of beats increases per second, then it becomes very difficult to be distinguished separately. Understand? Solve them separately. So it is always better to have very less least difference. Maybe 1 hertz, then 2 hertz, that will be clearly audible. So what I am talking about is about sound only. The same thing can happen in many electromagnetic wave. In that case, detection is possible with a certain sensors, special receivers are required. Then also such beats can be recorded. Okay, so we can say that beats are the periodic variation in the intensity of the amplitude of composite signals when two sinusoidal signals of slightly different, okay, you have to underline it, slightly different frequencies but identical amplitudes are superposed together in a medium. Okay, you need two different waves, slightly different wavelengths. When they superpose, they form beats. So in B formation, we will see alternate variation in sound intensity. Okay, this variation in sound intensity will be equal to the difference in the frequency. Okay, a difference in the frequency indicates how many times that intensity can be heard in 1 second. Okay, so hope this idea is clear. And beats has so many applications in different arenas of technology and science. Even in music it is used. Okay, you can see here one of the applications of beats are used in musical instruments like the guitar. It gives some special effects. One of the applications. And you know, they are also used to tune certain musical instruments. Certain musical instruments frequencies are tuned precisely using the concept of beats, and they are also used to determine frequency of tuning fork. Because suppose we are given with two tuning fork, one of them is known, one of the forks frequency is known, and second one suppose it is unknown. You can produce beats and you can find out the frequency of the unknown tuning fork. We have a problem like that, a numerical problem. We will do it in which this concept is used. And this is also used in instruments like a sonometer. Okay, sonometer is a very important device used in the physics lab where to calculate the resonance length and even sound velocity. We use the concept of beat formation. And it is also used in mines, okay, mines and other tunnels to detect harmful gases, where they are using some electromagnetic wave. And beats are formed using electromagnetic wave, and the beat detection can be indirectly used to detect certain harmful gases. Okay, these are some of the typical applications of beats in our applications. Here is now the time for question assignment. Here is the first question. When two waves of slightly different frequencies and identical amplitude propagate through a medium and superpose, prove that. Okay, you have to prove that the frequency of the resultant wave is the average of two wave frequencies. That is f1 plus f2. Right? We have already discussed it. You have to write it. Okay. Second question is you have to prove that the intensity of the resultant wave will peak to maximum at the rates equal to the difference of the frequencies of the waves. Okay, this thing also we have discussed. You can definitely write it. You can definitely surely write it in different ways. You can write it. Okay, so this is an important chapter. This is an important topic as far as your examination is concerned. As well as in any physics, you need this too much, too heavily, in order to discuss, in order to explain many other phenomena. This is the basic reference method. Okay, and here is the second question for you. And of course, this is taken from the famous book Halliday and Resnick. Question is like this: a tuning fork T1 of unknown frequency makes 3 beats per second with a standard tuning fork T2 of frequency 384 Hz. Okay. The beat frequency decreases when a small piece of wax is put on the prong of the first fork. What is the frequency of T1? Okay. Also, calculate the wavelength of the sound produced by T1. Velocity of the sound is given here. It is 333 meters per second. You can easily find it because it has two parts. One is the finding the frequency of the first fork. How you will find it? It is mentioned that when a wax is placed over it, what happens? Beat frequency is decreasing. Beat frequency decreasing means what? Frequency of the first one should be greater than the frequency of the second one. Okay. I hope this clue is enough for you. Frequency of the first one is greater than the frequency of the second one, because difference is decreasing. The problem says that difference is decreasing. So what does it means? Otherwise what should happen? If first frequency is decreasing, then difference should increase. But here it is shown as difference is decreasing. That means the first frequency would be T1 should be of higher frequency than T2. Okay, with this clue you can do the first part, and the second shows calculate the wavelength of the sound produced. Of course, if once you get the frequency and you have the velocity, you can definitely find the wavelength. Okay, I am sure that you will enjoy to do these assignments, both assignments, very nice assignment. Do it with good plans, neatly and correctly. Okay, so again, once again reminded to watch the video at least twice, and also you are requested to subscribe the channel and place your likes and dislikes in the YouTube video. Okay, hope you enjoyed it. Thank you all. See you again.